Oh, this is like one of the best problems ever. Look at this. Okay, so let's see. We've got a mass. The mass of each particle is 1 milligram, right? Oh my gosh. So that is 1 times 10 to the minus third grams is 1 times 10 to the minus sixth kilograms. Wow. Each milligrams. Wow. Okay, I think that's right. And then they are 3.5 centimeters from each other, so that distance is 0.035 meters, right? And what we do, here's how we're going to do, is we're going to pretend like this charge is creating the leftmost one, then positive 9.5 e minus 6. We're going to say it creates a potential right here. Okay, so let's figure out that potential that exists where this charge is now. Okay, so let's find that potential. That is kq over r, right? So k times this divided by 0.035 times 9.5 e6 over 0.035. All right. Okay, so alpha k times 9.5 e6 divided by 0.035. Notice it's not squared because this is the, oh wow, that's a lot of potential. Okay. Oh yeah, because I did times 10 to the positive 6, so let's try that again. Negative 6, there we go. Okay, still a lot, but not quite as much. Okay, so it's very unhelpfully 2440142 point a bunch of stuff, right? That's the potential at this point, right? And that's positive, right? Okay, so now the work I did to put it in that position, okay, we actually have a formula for this, right? So the work, if I take this charge and I start it over here at infinity, which is very far away, and I move it to that spot right there, the work that I would do would be, and they've got this formula in the data packets on like page 8, Q times VE. Now you never mind that they have the formula VE is work divided by Q, right? They also give us this formula, but they don't give us the formula for electric field, so go figure. Okay, so the moved charge, remember this is the moved charge that you use for that, right? The moved charge is the other 9.5 microcoulomb charge, right? So I'm going to go times 9.5 e minus 6, and I get that there's the work was 23.18 joules of work to push this guy into this position. And all I did there was I multiplied this charge by this potential, okay? And I got that amount of work, right? So now here this thing is, it's got this much energy, right? And they are released at the same instant, okay? So this is just, the funnest problem, right? We could make this problem so much harder. That is, I could release this one and a half a second later release this one. So this one would have gotten some velocity, and then we'd have to figure out what that velocity was and all that stuff, right? Or the other thing that would be fun is that what if they didn't have the same mass, right? Well, then, what's going to happen here is that this potential energy is going to turn into kinetic energy, right? If they have the same mass and they are released at the same instant, they share this energy equally. If they don't have the same mass, they don't share the energy equally, but they do share the momentum, right? They'll have a net momentum of 0, right? And then if they're released at different times, that's fun too, right? But this is the simplest one, right? In the simplest case, we can take this energy, the total energy of the system, the 23.18, divide by 2, and then that's going to equal the kinetic energy of each one, right? 1/2, 1 e minus 6 v squared. We ought to be able to solve for v, right? Because each one gets half that kinetic energy. Alrighty, that's a good problem.